The next paper to present it in this session is Hybrid Fuzzy Evaluation Algorithm for Power System Protection Security Assessment. Presentation will be given by Georg Janick Meyer. He is a PhD student at Friedrich-Alexander University in Erlangen-Nuremberg. So his topics are evaluation, optimization of protection system coordination, and the use of artificial intelligence in protection. So Janick, please start your presentation by screen sharing.
Thank you, Professor Gablik, for the nice introduction. I hope you can hear me. Yeah. All right. Is it okay if I do not share the screen, but use the camera? I will switch to my presentation and everybody has to use the presentation mode. Okay, I hope you can all see the presentation slide, the first one. And if you switch to presentation mode, it will be big. So I will start my clock. Yeah, thank you for joining today at this session. And I would like to start with a serious question concerning our security of supply. Is our protection and network security in danger? Distribution grids worldwide are confronted with higher enforcement of power electronics, shorter time constants, and an increasing number of prosumers participating in the market. Volatile sources and the increasing use of flexible AC transmission systems led to changing load flows and thus to different and time-dependent fault situations. Especially protection relays are disregarded in these times, even though incorrect settings of not adapted relays have led to numerous major events in the last 2 decades. Just to name the most important ones, we got, for example, the USA-Canada blackout and also the Italian blackout in 2003. The European system separation in 2006, India blackout 2012, Turkey blackout 2015, South Australia blackout 2016, Brazil major load shedding event 2018, and so on. Even if we haven't had any major event in 2020 so far, the year is not over yet. An easy and effective solution to those events are frequent and quick assessments and necessary optimizations of the protection system coordination after major changes to ensure correct functionality. So let us take a closer look on the most common types of protection relays used in the distribution and also transmission grid with backup functionality, which are the distance and overcurrent protection. The distance protection principle is based on the evaluation of voltage and current and calculates the resulting fault resistance and reactance locally at the point of installation. Based on the known reactance of the surrounding equipment, the distance from the relay to the fault can be determined. If the fault occurs, the own protection area, the relay should trip immediately. Otherwise, it can work as a time-delayed backup for following relays. Safety margins are usually considered of 10 to 20% to the end of the next protection area to ensure selective tripping. In the shown grading chart on the left side for a radial network, different zone lengths for distance protection relay R1 are shown. It can be seen that using standard equations to calculate the zone lengths, the zone reach of X3 of relay R1 is overlapping with X3 of relay R2. So that could cause an overfunction. At the lower line, the zone reach X3 of relay R1 is too short. So relay R4 has no backup protection, which could cause an underfunction. Overcurrent protection relays are the most common relay types and are available with various timing characteristics to coordinate with other protection relays. The picture on the right side shows the grading chart for an overcurrent relay with 2 tripping stages. To prevent unselective tripping during normal operation, the overload stage must be higher than the highest load current that can occur. The short circuit stage depends, of course, on the short circuit level and must be coordinated also with subsequent relays. Okay, so far so good. Sounds like a simple task to coordinate both protection principles. But let us take a closer look on reality with a little example I've got on the next slide. Especially in the practical use of distance relays, a number of influencing factors that adulterate the measurement result must be taken into account. In this figure, a simple grid model is shown. If all three switches S1, S2, and S3 are open, we actually have just a stub line fed by the connected source on the left side. This makes it easy for the distance protection relay R1 to calculate the correct distance to the fault occurring on line BC. But if we close, for example, switch S1, the relay R1 measures just half of the actual short circuit current supplied by the source, and this leads to a higher reactance measurement. The relay R1 assumes the fault to be much further away than it is, which can be seen from the red line, number 3. Similar negative effects for measuring accuracy can be noticed if other switching stages are analyzed. In this case, for example, also number 2, number 4, and number 5, depending on the switches. So the question is, how do we review protection system security? The traditional approach is that protection system experts are using various grading charts of protection relays to coordinate everything. However, this method has various disadvantages. First of all used graphical depictions are incomplete from an overall system perspective. Diagrams are for one network state and do not support the detection of cascading faults. Without an automated solution, it is impossible to perform systematic protection system reviews on a regular basis. That's why the Protection Security Assessment tool, short PSA, from Siemens has become known in recent years. It simulates numerous short circuit simulations together with the protection system behavior to assess the response of all relays in a system-wide grid. At the end, the result is plainly visualized as it can be seen in the picture here in the middle, and weak points or bad relays can easily be found. Pretty much the only downside is that the system is not able to generate better settings on its own. For this task, an expert is also needed. So at this point comes now our new hybrid fuzzy evaluation algorithm into play. It also bases on simulation data. It is a system-wide assessment tool, delivers relay-dependent evaluation values, and through optimization algorithm, it is possible to generate the best possible settings of all relays in the system-wide grid to the same time. So let's take a look on how it works. Traditional approaches are using the resistance and reactance of the connected equipment as reference data to calculate the individual setting for each relay. But as already explains, various effects are influencing the measurement results. So in order to take all possible eventualities into account, a systematic fault analysis is done in advance to generate realistic and reliable reference data based on simulations. Depending on the required attention to detail, every X% of every line of the grid, a short circuit fault simulation is carried out. For each individual simulated fault, all measured fault impedances and all fault currents of all relays are recorded. The measurement result of each relay is then assigned to the respective protection area of the relay according to the responsibility for the fault. Let's take a closer look on the diagram. We can see that a fault occurs on line DE. Directly connected and therefore responsible for that fault are the protection relays R5 and R6. So these relays store the simulation result in their own protection area 1 list. The backup relays R3 and R7 are seeing the fault in forward direction and store the measurement result in their protection area 2 list. The relays R1 and R9 provide backup for the relays R3 and R7 and store their values in their protection area 3 list. This process is repeated for all topologies in all possible states of the grid. Thus, all eventualities and electrotechnical phenomena can be taken into account automatically. At the end, all results are merged and form the underlying reference data for the following evaluation strategy. Two of the most important criteria when assessing power system protection are dependability and security. Dependability is defined as the degree of certainty that a protection relay or a system of protection relays operates correctly. In contrast, The definition of security is that a protection relay or a system of protection relays does not operate incorrectly. Specifically, this means that dependability indicates whether protection relay trips when it's necessary. Security, on the other hand, is the ability to avoid unnecessary tripping behavior in all operation conditions, as well as short circuits and faults outside of the relevant zones, and is therefore closely linked to the notation of selectivity. The edge between dependability and security of a protection system is usually narrow, especially since both criteria make conflicting demands on the setting values. The new evaluation strategy bases on the fuzzification of the criteria dependability and security using two different membership functions. Fuzzy sets extend the assessment of membership of elements to a set from bivalent to gradual. Therefore, the membership is described not only by 0 for not belonging and 1 for belonging, so not just it is selective or it's not selective or it's dependable or not dependable, but it's any number as a degree of affiliation possible. So we can assign a setting value to both criteria to the same time. This kind of consideration is now applied to the setting elements x1, x2, and x3 of distance relays and the overload and short circuit states of overcurrent relays. They are assigned to the membership functions dependability and security, and we call this process fuzzification. It makes it possible to express independently the quality of each setting over a degree of belonging. The graphs of the membership functions are sigmoid functions as shown in the picture right here. The function bases on the previously created simulation data and also depend on the settings of the surrounding protection relays. That means that the sigmoid functions of every setting looks different for every relay, and that a change of setting values of one relay will therefore also lead to new membership functions of other relays. If we combine all fuzzy sets together, then we form a multi-criteria optimization target. And this function, this output function, can be seen as the quality index of the whole protection system. Yes, and this type of construction, thus represents a function we are able to optimize using an optimization function. Proven to be efficient, we used an EPSO-DE particle swarm algorithm, which was first introduced in 2016 at the PSEC in Genova. It is a hybrid heuristic optimization algorithm combining the advantages of evolutionary algorithm, differential evolution, and particle swarm optimization. The algorithm optimizes all fuzzy sets of all settings of all relay simultaneously. We applied the hybrid fuzzy evaluation and optimization on an adapted version of the IEEE 9 bus grid to find the best possible setup. The IEEE 9 bus grid was adapted to have more realistic influences on the protection system through the added parallel line and changed lengths of the transmission lines. In addition, 2 stub lines were added and the loads distributed. All transmission lines are protected by 2 distance relays at the beginning and end of each line. Just the stub lines are only protected by 1 overcurrent relay at the beginning of the line. The generators get protected by an own overcurrent relay. To verify the effectiveness of our new hybrid evaluation and optimization strategy, we used the proven PSA method of the program PSS-Syncal to evaluate the optimized settings and compare it to the evaluation of settings calculated by adjustment rules based on equipment data from equation of the literature. It can be clearly seen that the results of our new evaluation method on the right side performs significantly better. Almost all short circuits were cleared selective, and just a few faults were cleared with an overfunction, but that concerns just the backup protection if primary protection fails. So to conclude, the new hybrid evaluation algorithm for protection security assessment uses reliable simulation data as underlying reference data to build up its fuzzy sets. Using the evaluation criteria, dependability and security, all protection relays of a system-wide grid can be assessed with the same evaluation method. Every setting of every relay has its own fuzzy set, but all sets are combined to one protection security index. Using an efficient optimization algorithm, it is possible to find the best compromise in complex grid structures and the best settings for all relays simultaneously. Validated by the proven PSA method, our new approach is able to improve system security. Yeah, thank you very much for listening. And if you have any kind of questions, then please feel free to ask them now. Thank you.
Thank you, Janick, very much for the timely and very nice presentation. So there is one question. Is this solution applicable in the presence of converter interface generation units like wind power types 3 and 4?
Yes, because we are just using simulations. So dynamic simulation, actually, we can simulate those converters too, and they will just produce additional data for our underlying data we can build up our fuzzy sets on. Yeah.
Okay, thank you. So there are no more questions in the Q&A, but I would have another question. So I understand that the methodology is suitable, and you showed that the protection settings can be improved. What would have to be done to say that they are optimized so that there is no better solution for protection settings? Would that even be possible?
No. Yeah, so if you combine all fuzzy sets, it is getting so complicated, and it's such a complex task. You have to use an optimization algorithm, and we use the heuristic, and heuristic optimizes usually really, really good, but you never can say you have found the best setup that exists. If you want to do that, you have to, you have to be sure, calculate everything, then you know what's best, or you use different methods, but that won't work because it's too complex. But okay, you can find a solution which is probably good enough, and that's of course what we want.
Okay, thank you. I fully understand. Appreciate. Thank you for your presentation again and for answering the questions.